Okay, so for about 100 years, there's been one rule in physics we thought was unbreakable. Nothing, and I mean nothing, can go faster than the speed of light. It's the ultimate cosmic speed limit. But what if something was breaking that rule? Not just as a weird exception, but like all the time. Well, that is the shocking reality we are diving into today. And no, this is not science fiction. This is a real quote, a conclusion that experiments have literally forced us to accept. So we're going to unpack exactly what that means, because it is without a doubt one of the strangest and most profound truths about the universe we live in. So how? And what on earth does that mean for reality itself? These are the huge questions. And to answer them, we need to solve a mystery that pitted the absolute greatest minds in physics against each other. So think of this as a cosmic detective story. Our story, of course, starts with our main character, Albert Einstein. I mean, this is the guy who is the architect of our entire understanding of space, time, and gravity. But even he found something absolutely terrifying hiding in the new theory of quantum mechanics. Now, to get why he was so worried, you gotta understand this core idea called locality. It's actually pretty simple. Imagine the sun just, poof, vanished right now. We wouldn't know for 8 minutes. That's how long it takes the light and the gravity to get here. Cause and effect have a speed limit. It's a fundamental pillar of physics. And this is where it gets wild. Einstein showed how quantum mechanics seem to just completely ignore this rule. He imagined a single electron. Its position isn't fixed, right? It's more like a wave of possibilities spread out over space. But the very instant you detect that electron in one specific spot, its wave of possibility everywhere else has to vanish, instantly, no matter how far it had spread. That's what Einstein called it. To him, this was a massive red flag, an effect here, causing an instantaneous change way over there. He famously called it spooky action at a distance, and he was dead set on proving that the quantum theory must be missing something. And just like that, you've got a major showdown, two completely competing explanations for this spooky behavior. You could even call it a duel between two different versions of reality itself. So on one side, you've got Niels Bohr. He basically said, look, reality just is non-local. This spooky connection is a fundamental part of how the universe works. Get used to it. But on the other side, Einstein argued there must be some hidden variables, some deeper information we just can't see. His thinking was kind of like this. If you have a pair of gloves and you put them in two separate boxes, the second you open one box and see the left glove, you instantly know the other is the right glove. Not because of a spooky link, but because that information was baked in from the start. Einstein and his colleagues, Podolsky and Rosen, they really sharpened this argument with what's now called the EPR paradox. You create two entangled particles with opposite properties. You send them flying apart. The moment you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. So how does that second particle get the message faster than light? And for almost 30 years, that's exactly where things stood, a total stalemate. You see, the problem is that both Bohr's spooky universe and Einstein's hidden information universe predicted the exact same results in every experiment. There was simply no way to test who was right. It wasn't science, it was just philosophy. Yeah, the case went cold for decades, but then, in the 1960s, a brilliant physicist named John Bell came along. He was the detective who finally figured out how to put these two realities to the test and crack this case once and for all. Bell's idea was it was genius. He realized that if you measure the entangled particles but along different, randomly chosen angles, you could set a trap. It's like this. If Einstein was right and the particles had hidden instructions, there's a limit to how well they could coordinate their answers when you ask them these tilted, random questions. But if Bohr was right and they were spookily connected, they could coordinate in ways that would defy that limit. This twist finally forced the two theories to predict different numbers. Okay, so here's the first prediction. This one is from Bohr's spooky, non-local reality. The math showed that these mysteriously connected particles would be so perfectly in sync that even when measured at different angles, their results would disagree only a quarter of the time, just 25%. So remember that number. But, and this is the brilliant part, Bell proved that if Einstein was right, if reality is local and there's no spooky stuff going on, then there's a hard limit. Those particles, with their hidden instructions, just couldn't do any better. He calculated that any sensible, local theory must have a disagreement rate of at least 33%, 1/3. So there it was, for the very first time, a clear, testable question. 25% or at least 33%? The answer would tell us which universe we actually live in, Einstein's sensible one or Bohr's spooky one. So, what did the experiment find?
And now, we have arrived at the verdict. The experiments were run, the data came pouring in, and the results were, well, they were in.
The results was absolutely breathtaking. I mean, just look at this. Experiment after experiment confirmed the quantum prediction. The actual disagreement rate found in reality was right around 25%, completely smashing through that 33% limit required by Einstein's sensible local universe. Einstein was wrong. The conclusion is inescapable. The universe is fundamentally non-local. That spooky, instantaneous connection that bothered Einstein so much isn't a flaw in the theory. It's a real feature of our reality. And this quote just perfectly captures the fallout. We are obliged. We have to accept it. There are influences in our universe that travel faster than light. Einstein was right to be spooked, but he was wrong about what it meant. The spookiness is real. So where does that leave us? What does this actually mean for physics and for us? This is where the implications start to get truly mind-bending. The first question everybody asks is the obvious one, right? Can we use this to build a faster-than-light telephone? Can we send signals into the past and totally mess everything up? And the answer, amazingly, is no. You see, while the connection is faster than light, the outcome of any single measurement is totally random. You can't force your particle to be spin up just to send a 1 to your friend across the galaxy. Because you don't control the outcome, you can't actually send information. So the ultimate speed limit is safe, but it's a very, very uneasy truce between these two giant ideas in physics. But there is one last wild, absolutely bizarre escape hatch. Bell's entire proof rests on one tiny assumption, that when you make a measurement, there's only one outcome. The many worlds interpretation just throws that idea out the window. It says every time a measurement is made, reality splits. Both outcomes happen, each in its own brand new parallel universe. And if that's true, well, there's no collapse of a wave and no need for any faster-than-light signal. And that leaves us with this final, staggering choice. Is our universe fundamentally non-local, filled with these spooky connections that defy all of our common sense? Or, to save Einstein's sensible local reality, do we have to accept that we live in a constantly branching multiverse of infinite parallel worlds? That is the profound and frankly awesome question this whole mystery leaves us with.